So if we look at this projectile, doesn't matter what it is, what's important here is that it's being launched with some kind of force that's going to give it a velocity, right? Because if there is no velocity there, that sucker's not moving. So it's going to be launched with some kind of velocity that's basically going to shoot out straight this way, okay? And that velocity will be launched from an angle to whatever surface. Could be on a cliff, could be on the ground, doesn't matter. Now, this type of projectile motion really does take in absolutely everything we've learned this year. It takes in vectors, it takes in URM, and it takes in free fall. Okay, it's a combination of the three big things we've learned. Why does it take in vectors? Like, why are vectors a part of this? If we look at this image, okay, that red arrow represents what in this situation? It's going to represent our VI, right? So the red arrow is going to represent our initial velocity. But here's the thing. The initial velocity here has not been attributed to the y-axis or the x-axis. It is the resultant, this numerical value for this actual velocity is the resultant of the x component of the velocity and the y component of the velocity. Okay? So that's the same thing as saying VI squared is going to be equal to what? VIX squared plus VIY squared, right? So when we look at these vectors, the reason that we have to use that component method here is that you're going to be given an initial velocity. And you're going to be then asked from this velocity that is a combination of x's and y's. Okay? This is a combination of a velocity in the x and a velocity in the y. This number. And you're going to be asked to use that as a variable when you're either solving y questions or y components, or you're solving x components. And you cannot use the number as is. So if this is, let's say, 30 meters per second, this initial velocity, this 30 meters per second, involves not only its horizontal velocity, or its VIX, or just its VX in general, because it doesn't change, but it also incorporates its VIY. And if you're going to calculate the maximum height of this projectile, or the time it takes to reach its height or its range, you cannot just use the combination of the x and y. You have to use either the VIX or the VIY, whichever of these two you're actually working with. So if we're looking at using things that are on the horizontal, what are some of the things we can solve on the horizontal? We could solve for, we could solve for range. Okay, this is x, absolutely. What else could we solve for? In the x, what else could we solve for? We could solve for the time it takes to actually get from here to here. Sure. Anything else? If we know our VIX, do we know our VIY, our VFX, sorry? Yes, we do, because it's URM. Is there any acceleration? No, there is not. Now, when we want to work in the y, what are things that we can actually calculate in the y? What are things that we can figure out in our y here from this projectile? We could figure out its maximum height. Absolutely. What else can we figure out? Well, its acceleration is always the same, right? Acceleration is a given. It's always going to accelerate at negative 9.8 meters per second squared. We could calculate the time. that it actually takes to reach its maximum. Okay, now interestingly enough, there's a relationship there because the time an object takes to reach its peak height is exactly half of the distance that ends up getting covered. Because what goes up must come down. It starts coming down once it gets to the halfway mark. It's going to take it a certain amount of time to reach that pinnacle and the same amount of time to come back down. So if for some reason you don't have enough variables to calculate its actual range or the time it takes it to complete its whole horizontal motion, you can calculate the time it takes for it to reach its max and just double it. Because if it takes it 2 seconds to get up, it's going to take it 2 seconds to come back down. Okay? In addition to having your initial velocity, you can calculate the velocity at which this object is going to come down at. Okay, this is your final velocity. So now, interestingly enough, your final velocity is not, it's going to have the same x component as your initial velocity did. What do you think what kind of little, I guess not analogy, but what kind of little relationship can you actually come up with here in terms of initial and final velocities? If something is launched at an initial velocity of, let's say, 30 meters per second, what will be its velocity once it hits its max height? It will be 0. For that fraction of a second, its velocity will be 0, and then it'll start, its magnitude will start increasing again as it nears the Earth, right? Because of gravitational acceleration. In theory, once, just before it hits the ground here, if we were to clock that velocity, we would see that the magnitude should be the same. The magnitude should be the same. The direction, however, will not be the same. Okay? If I look at this image, and we're talking about the fact that your final velocity, the velocity that the object has just before it hits the ground, is a vector. It's a combination of your x and y, because look at its direction. It's at this angle. It's coming down from here, and it's coming down straight. That is not horizontal or vertical. It has an aspect of each. Okay? It's got the horizontal component here, and it's got the vertical component here. So this is going to be your v xf, and this is going to be your v yf. We know that the v xf is going to be the same as the v xi, or the initial velocity in the v, or in the x, because it doesn't change, it's URM. But the v final in the y is not going to necessarily be the same. Now in this case, when a projectile is launched from the ground at an angle, and it comes to the ground at an angle, then yes, their magnitudes will be the same. Okay? Their magnitudes will be the same, because what goes up at whatever rate will, assuming no air resistance, will come down at whatever rate. How many of you do track and field and you do the javelin throw? Okay, throwing a javelin is, in fact, launching a projectile at an angle. That's what you're doing. That projectile, you're trying to get the maximum distance for the power in which you're adding that to that actual spear. Okay? Now, in terms of whether VF is the same as VI, when you're on a horizontal like this, when you're on a flat surface, yes. But what happens all of a sudden if, let's say, you launch something from here and then it goes down here? In theory, if you were launching it on a horizontal, the horizontal would end there. But it doesn't. As it keeps falling, it's going to have a faster, faster, and faster velocity. Okay? Due to gravitational acceleration. So in this case, it will not have the same VI as it does VF. And that is where breaking down your components is going to be really important, because it's not automatically going to be the same. Do you think that this VF down here will be greater than the VI up here? Yeah, of course it will, because it's had more time in the air and it's had more time to accelerate. Okay? Now, in terms of its direction, okay, I want to just zoom into this, and I want to say, let's talk about the vectors here. So if I've got my ledge here, and I've got my projectile leaving, the angle here, okay, is going to be in what quadrant? It's quadrant 1, right? So it's going to have a positive x and a positive y, right? Absolutely. This vector is going to take off like this. That is my VI. I can break down my VI into my VXI and my VYI by doing my cos of my angle and my sine of my angle for the y, right? That's vectors. Now, when this guy here crashes to the ground, we have to look at its direction. So if we move this up, move that over, let's draw this out over here. If this is our ground, okay, and the projectile is coming down like this, let's say. It's hitting the ground right there. Okay, so it's coming in this direction, right? Well, when you measure the angle of an actual vector, do you measure it from the tip of the actual vector? No, you don't. Okay, so what you would do, if the ground is your horizontal surface, if that's your x, if you just keep this going like so, that's the direction of your actual vector, is it not? Draw yourself a little grid right here. And then you can actually determine that this is the angle of the final velocity.
Oh, you did the full, okay.
Okay? Well, yes, that's how you measure theta. Woof, that's a long time ago. Okay, when we measure theta. But you could easily calculate, if you do your tan, if you do inverse tan of the y component over the x component, that's going to give you your alpha. Your alpha is this guy right here. Right? You're going to do your x and then your y. That's your alpha. You could subtract that alpha from 360 degrees. And you will get the theta or the direction. Now, you might notice something. The direction should have some kind of commonality to the direction of the initial of the initial velocity. It should have the actual same number in terms of its degrees, but it should be whatever that number is minus 360. So if, let's say, that was launched at, I don't know, let's say it was launched at 30 degrees or 45 degrees, it will land at 45 degrees minus, or negative 45 degrees. Do you understand what I mean? Yeah?